Look around you. The trees, the rivers, the land, the air, the ocean, the mountains, the biodiversity. Are you proud of these wonderful sights? Of course you are. But are you proud of what we have done to them?
Agriculture is at a great risk due to climate change as crops are directly affected by plant diseases, costing the global economy billions of dollars and threatening the global food security. Rising temperatures, irregular weather patterns, and increased pests and diseases pose major challenges to farmers worldwide. These challenges lead to reduced crop yields, threatening the availability and affordability of food for communities around the globe. According to FAO 2021 report, pests and diseases outbreaks destroy to 40% of global crops and cause $220 billion in losses. On the other side, weeds are one of agriculture's most significant biotic constraints. They not only reduce crop productivity by competing with crop plants with nutrients, but act as alternative hosts for insect pests and disease-causing pathogens. In our daily routines, we often overlook the impact our habits can have on the environment. Every choice we make can contribute to climate change, from the energy we consume to the waste we produce. Simple actions like leaving lights on when unnecessary, using single-use plastics, and wasting water contribute to increased carbon emissions and environmental degradation. The lack of awareness about these impacts further aggravates our challenges in combating climate change. To address these problems, we decided to develop our project. Together, using AI and IoT technologies, we came out with an empowering mobile app and an intelligent agriculture system that will help mitigate the effects of climate change on the agriculture sector and decrease the crop losses and raise the awareness about climate change by providing the users with a platform to share their knowledge and tools to take action and make the change.
Our project consists of two main parts. The first one is Smart Farming System, which offers three primary services through a web-based system using IoT sensors and deep learning models. First service is an intelligent weed detection system that helps to reduce the presence of unwanted weeds in the crops as they compete with the main crop and affect its growth. The deep learning models used in the service are based on two fine-tuned pre-trained models, which are ResNet-50 and EfficientNet-P2. They can automatically extract high-level features from images and classify the weeds at different growth stages. And to make this possible, we have trained the ResNet-50 fine-tuned model on the cotton weed dataset, which consists of 5,187 images of 15 common crop weeds that are common in cotton and other crops such as wheat and maize. For EfficientNet-P2 model, we have trained it on the plant seedlings dataset consisting of 5,545 images of plant seedlings from 12 different classes divided as 8 seedlings correspond to wild weeds and 4 seedlings that belong to common agricultural crops at various stages of growth to help the farmers to detect the weeds at early stages. The second service is the intelligent disease detection system that can identify 9 diseases in rice crops in the early stages to contain diseases before spreading and losing most of the yield. The model uses transfer learning, and with the fine-tuned ResNet-34 pre-trained model, the system classifies the disorder from the imagery data. Imagery data can be collected from any image source as mobile phones, drones or rovers from the crop fields and via our smart farming website. The images are uploaded to the back-end cloud server and AI models start to process the data to identify the weeds and the diseases and return the results to the user dashboard. Finally, our last service, the IoT-based crop recommendation and support system, will assist farmers in selecting the most suitable crops for each season based on soil nutrients and climate variables, and provide precision agriculture with insights to help them save their crops and increase productivity. The system relies on random forest classifier model that predicts the most suitable crops to grow based on temperature, soil pH, NPK values, humidity, and rainfall rate. We have implemented 3 algorithms for the support systems that provide data-driven recommendation for achieving optimal nutrient and environmental conditions to improve crop yield. It gives the farmer soil health insights during the whole cultivation season, and it determines the land's nutrients needs based on the nitrogen, phosphorus, and potassium values received from the sensor and the land area. The system recommends the required amounts of soil enhancers such as urea and compost if needed. The sensors have been implemented in the soil collected data and sent it to the edge computing device, which is the Arduino Uno in our case, that in turn transmits the data to the backend cloud server through the internet to be processed, and the results are sent back to the end user dashboard.
The second part is the empowering mobile app, which provides 3 main features. The first one is the Smart Planting Guide. This tool makes planting easier by utilizing deep learning models to predict and recognize the plant's type, either from the plant's leaves or flowers, to offer user comprehensive information on how to properly care for the plant, and with the ability to add their favorite plants to their garden. To achieve this feature, we developed 2 models. The first one is to classifying plants based on the leaves features. We have developed a linear discriminant analysis classification model that finds a linear combination of features to separate data into classes, capable of classifying 99 different types, as we have trained our model on a leaf dataset that consists of binary leaves images and extracted features including shape, margin, texture. It was challenging to pre-process the user image to extract the feature manually. Like in the training dataset, the pre-processing involves various methods, including the calculation of statistical measures, texture analysis, and shape analysis. For the flower classifying model, we have developed a fine-tuned ResNet 50 model and trained it on a flower dataset that contains 16 types of flowers. As the dataset wasn't large enough to train our model with high accuracy, we applied some data augmentation techniques. We have also built a document database using MongoDB to provide the users with the plant information for each plant. The second feature is the community, a platform for people to share information and raise awareness about climate change, including a marketplace offering eco-friendly and gardening products. The last feature is pollution reporting, to enable people to report any polluting activity by only capturing an image. The report will contain the user's location alongside the image and will be sent to specialized authorities to take an action.
To develop our project, we have used a lot of technologies and frameworks. For the hardware, we have used Arduino Mega board connected to 7 sensors, which are temperature, soil pH, soil moisture, NPK sensor, along with the ESP8266 module to send data over the network. For the software, we have used Python 3.9 to develop our models using TensorFlow, PyTorch, and other common libraries. For the back-end, we have used Flask framework along with the save-to-train models, and we have used MongoDB to build the plant's information database. We have used the Flutter framework with Dart language to develop the empowering app, and with Fire-based services like authentication, Firestore, and Fire-based storage, we have handled the user information and data. For the web-based smart farming system, we have used React.js framework to build the front-end interface, and with JavaScript to handle the requests and display the result to the user dashboard.
Here is our high-level architecture showing the data flow for the empowering app and the farming system, and also the IoT devices which are connected to the Arduino board to send the data over the network using the ASP to the back-end cloud server, as we used the AWS services to deploy our Flask backend. The data are processed and the AI models make the predictions, and after that the predictions are stored at the Mongo database and sent to the user and the device instantly.
From the beginning, we thoroughly planned finding the project scope, goals, and user requirements. We broke down the complex project into smaller, manageable tasks, ensuring each sprint had well-defined objective. Throughout the development of our project, we embraced the agile methodology. This flexible and iterative approach enabled us to adapt and evolve our solutions to meet the dynamic challenges we faced during implementation. With the agile methodology, we emphasized continuous improvement and collaboration, placing the needs of our users at the forefront of our decision-making process during development. Our empowering app is designed to be accessible and user-friendly. It can be used by anyone interested in planting and learning, or anyone who wants to positively impact environment. Farmers and agriculture production companies can easily install our smart agriculture system to monitor their fields using the web dashboard to access real-time data and insights. Regarding applicability, our innovative agriculture system can be used in farms of all sizes, from small-scale to large-scale industrial farms. Our solution is scalable, and we're confident it can significantly impact the agriculture industry.
We're planning for further improvements to our empowering mobile app and smart agriculture system. One of our primary goals is to expand the app's features and functionality, making it even more impactful and engaging for users. We envision adding an interactive map to showcase the global impact of climate change, an event organizing feature, and introducing gamification elements to reward users for taking sustainable actions. Another aspect is scaling the app and farming system by collecting new data sets to cover more plant types and crops. In addition to the current farming system features, integrating the drone to collect data autonomously can help farmers monitor crop health and identifying issues more efficiently. The drone can be equipped with sensors and a camera that collect data on soil and crop health, which can be analyzed using AI algorithms to provide farmers with more specific and precise insights.